One of the main uses of derivatives in single variable calculus is to determine the extrema of a function. That is, where the function has its maximum and minimum values on a certain domain. In this video and subsequent videos, we're going to extend that idea to multivariable functions. And so our goal will be to find the extreme values, the extrema, of a multivariable function on a given domain. So we'll go ahead and start by giving a definition for the various extrema that we're going to look at. These should look mostly familiar. It's just a sort of a natural extension from a single variable function idea to multivariables. So our setup is the following. All right, so we need to be given a multivariable function, so let's call that f of x, y. And it needs to be defined on a certain domain. And so let's call that domain capital D. Right? And we'll see what, this D can be any region of the plane, but typically it'll be some kind of a geometric figure, some nice region. Right, so in that case, we're going to say that f of x, y, this function, has a global, or sometimes called absolute, maximum. At a point AB, if f of AB is greater than or equal to f of xy for all points xy in domain D. And so this is a maximum because f of AB is the largest value of all of these. And it's the global or absolute maximum because it's the largest value for everything in the domain. If we consider every point in the domain, this is the largest function value. And similarly, we'll say it has a global or absolute minimum at AB if f of AB is less than or equal to f of xy for all xy in the domain. So similar idea. Now we're looking for the smallest value in the domain, the smallest function value. All right, now these two kinds of values taken together are often referred to as global or absolute extrema. So if we're asked to find global extrema of a function, what we're looking for is both the global maximum and the global minimum. The global extrema are important, but they're not the only kind of extrema that we have. So we also will say that this function f of xy has a local or relative maximum at the point AB if f of AB is greater than or equal to f of xy for all xy in some region around point AB. And so in this case, notice we're not saying f of AB is greater than or equal to f of xy for all x or y in the domain. We're just saying that f of AB is greater than or equal to f of xy for all points xy that are close to AB. And that's why we call this a local maximum. If you're just looking locally or nearby that particular point, it gives you the maximum value. But there may be points further away that do have a larger function value. All right, but for local or relative maximums, we're just looking nearby. And similarly for a local minimum. So we also say that it has a local or relative minimum at AB. If f of AB is less than or equal to f of xy for all xy in some region around AB. And again, grouping together, we call these the local extrema. And so if we're looking for the local extrema, we want all of the local minimums and maximum around this domain D. All right, so here we have a graph of a surface, some function f of xy. Notice that the xy plane is actually horizontal here, and the z-axis is going vertically up and down. So we're looking at this from this graph from the side. But if we look at this, we notice that there is a point over here, which is the largest value on this entire graph. It's the highest value, the largest z-coordinate of any point. And so that point right there is going to be our global maximum. Right, that value is as large as possible. The function value there is larger than all the functions values at the entire domain of this graph. And likewise, over on the other side, down at the bottom, we have a point way down here, which is the lowest point, the most negative on the z-axis, and this will be our global minimum value. So our global minimum appears here. Now we have two other sort of places where something is happening. So one is right here, kind of above the global minimum. Right? We have sort of a peak there of our graph, but notice that it's not as high as our global max, but it is the largest value nearby. And so this is an example of a local max. Because it's the largest function value nearby that point, but not overall. And likewise on the other side, down at the bottom on the right, we have a local min at the very negative peak of that portion of the graph. We have the smallest function value nearby, although as we see that we have the global min over there that's much smaller when we move over, but that's further away. Right, so this kind of idea, this pictures what we're thinking about when we're looking for global mins and maxes and local mins and maxes. We're looking at these peaks, both positive peaks and negative peaks of our three-dimensional graph. Thinking back to single variable calculus and the study of extrema in that context, the first step for finding the local and global extrema of a function was to determine all the critical points of the function f. And so that's going to be the first step here as well. We just need to extend the definition of critical point to meet the multivariable function context. So we're going to define a point AB to be a critical point of our function f of xy. So we're defining critical point. So it'll be a critical point of f of xy if partial of f with respect to x at AB is equal to 0, which is also equal to the partial derivative of y evaluated at AB. So we want both of them to be, both partial derivatives to be equal, or if one or both of those partials is undefined or does not exist at point AB. Okay. So this is pretty much the same definition from single variable calculus. In single variable calculus, you wanted points where the first derivative was either 0 or didn't exist. And so here the only distinction we're making is that we want either both partial derivatives to be 0, or we want at least one of them to not exist at that point. Right, so very natural extension of the definition, and it turns out that they satisfy basically the same property that they do in single variable calculus. So we can pretty quickly get this theorem in terms of local extrema. So the theorem says the following. So it says if f of x, y has a local minimum or maximum value at an interior point AB of our domain D, and if our partial derivatives f sub x and f sub y are both defined, or they both exist at our point AB, then our partial derivatives at AB both must be 0. You saw a very similar theorem in single variable calculus, where it said if a function f of one variable has a local min or max at a point A, and if the first derivative exists there, then the first derivative must be 0. And so what this tells us is that if we want to try to find all the local mins and maxes of this function, what we need to do is figure out where the derivatives or the partial derivatives either don't exist or where they're equal to 0. In other words, find the critical points. Now, one thing I want to point out about this theorem is I did use a term that I've not used in the course before, and that is interior point. That will become clear when we do some examples. But just as a quick example to give you the idea here, suppose we had a function and we cared about the function values on some rectangle in the plane. Right? And by rectangle, I mean the four sides of the rectangle as well as what's inside of the rectangle. Right? In this particular case, we would say an interior point is simply one inside the rectangle and not a point on the actual boundary of the rectangle. So not a point on the four segments that make up the rectangle. And the same thing if we have some other geometric figure. An interior point is going to be something that is inside and not on the boundary of the domain. So we have to, at this point, take a moment and make a warning. Just like in Calc 1, there are points in single variable calculus where we have critical points that are not local extrema. And sometimes that is a sticking point for some people. And so we have the exact same issue here. And so our warning here is that not all critical points are local mins and maxes. There's actually other things that can happen. And one of those things that can happen is called a saddle point. So we're going to go ahead and define that. This has no analog really in single variable calculus. So we're going to say that f of xy has a saddle point at a critical point AB if our function f takes on values both larger and smaller than f of AB, in every region containing AB. So the idea of a saddle point, while we were able to define it in words, is best understood by looking at a picture. So here's a graph of a multivariable function that has a saddle point. And the saddle point occurs right on the z-axis, so this point right here. Okay. And so you can see that if we move in this curve in the direction of the y-axis, we're actually getting values that are smaller. All right, so I can't draw that on the backside there. But if we look sort of along the y-axis in that direction, this point would appear to be a maximum value because all the points along that in that direction, all the other function values are smaller than that. However, if we look along the x-axis in that direction, then this graph looks a lot like a minimum. Right? This graph at that point goes up on both sides. And so in this case, this particular point, around this point, in any region that we take of our domain that contains that point, we're going to have some points that have a smaller function value, the ones along the y-axis, and we're going to have some function values with some points with a larger function value. And there's no way to make this either a maximum or a minimum. It is in some sense, in certain directions, it is a maximum. In certain directions, it's a minimum. And that is exactly what a saddle point represents. You could also see in this picture why it is called a saddle point. This particular graph and how they chose the domain, this really does look like a saddle. So let's look at a couple examples where we have to determine local extrema of functions. All right, so first, let's say we want to find the local extrema of the function f of x, y, given by x squared plus 6x plus y squared minus 2y plus 5. Our first step is to determine all the critical points of this function. And so to do that, we need to compute its partial derivatives. So f sub x, the partial with respect to x, is going to be 2x plus 6. And f sub y, the partial with respect to y, is going to be 2y minus 2. So these partials are very, very quick to compute. Now notice at this point that both of these partials will always exist. These are both just polynomials, and so there's no undefined issues. So the only critical points that we're going to get are ones where both of these partials are equal to 0. All right, so we need to set each of these partials equal to 0, and we need to remember that we need both of these things to be true. We need both partials to be equal to 0. And so these are quite easily solved. 2x plus 6 equal to 0 will give us x equals negative 3. And 2y minus 2 equals 0 will give us y equals 1. And so in this case, we only have one critical point, right? We want all the points that we get by letting both of these equations be true. And so here we only get one, and that is the point negative 3, 1. It's the only point with an x-coordinate of negative 3 and a y-coordinate of 1. So we know this is the only possible local extreme value for this function, but we really don't know if it's a local min, a local max, or a saddle point. And so we need some way of determining which one this is. Now later on we'll come up with a better way of doing this, but this function is very, very nice, and we're able to use the particular form of this function to determine this algebraically. So to start, let's compute the function value of f of negative 3, 1. Right, so if I replace that, it looks like we're going to get 9 minus 18 plus 1 minus 2 plus 5. And this yields a function value of negative 5. All right, so our function value here is negative 5. So now we want to do some algebra with our function itself. All right, so our function is x squared plus 6x plus y squared minus 2y plus 5. And because it looks like we have sort of two quadratic expressions here, one in terms of x and one in terms of y. And so we could go through here and complete the square in both x and y. And so when we do that, we're going to have x squared plus 6x plus 9 plus y squared minus 2y plus 1, and then plus 5. Now, this is not equal right now because what I've done is I've added 9 and I've added 1. So I've added a total of 10 to this. So I'm also going to subtract 10 from the constant over here. Okay. And so when we group this now, we have x plus 3 quantity squared plus y minus 1 quantity squared minus 5. Right, so we've been able to rewrite this equation in this particular form. And now what we notice is that these first two terms, it's the sum of two squares. So these must be combined greater than or equal to 0. Right? It's possible that expression is exactly 0, if that's if x is negative 3 and y is 1. But otherwise, this is going to be bigger than 1. Or sorry, bigger than 0. And therefore, the entire function, that thing minus 5, is always going to be greater than or equal to negative 5. Okay? So this whole function, for any x and y we pick, we're always going to get a value greater than or equal to negative 5. But remember, a little bit ago, we just computed f of negative 3, 1, and we saw that that was actually equal to negative 5. And so we've shown that negative 5 is the smallest possible value this function can take on, and it takes that on at the point negative 3, 1. So the conclusion that we can draw is that f of xy attains a local minimum at the point negative 3, 1. And in fact, what we've actually shown more than that. We've actually shown this is going to be a global minimum as well. Because we've shown above that f of xy is always greater than or equal to negative 5, not just nearby. So let's take a look at one more similar example. So let's say we want to find the local extrema of the function f of xy equals x squared minus y squared. So we follow the same approach to find local extrema. We want to first locate all critical points. So we do that by finding the partial derivatives. So in this case, f sub x is going to be 2x. F sub y is going to be 2y. Negative 2y. And we look at those, and it's very clear that these are always going to be defined, so we have no issues where these will be undefined. And so what we need to know when each of these are equal to 0. And this is actually easier than the previous one. These will be 0 only when x and y are 0. And so we only have one critical point, and that is at the origin, 0, 0. So this is our only possible value, only possible local extreme value. But again, it could be a local min, a local max, or it could be a saddle point. And so in this case, unlike the previous example, we don't have any nice algebra that we can do in this particular function. But what we could do is we could approach the origin along different curves. So for example, I might want to approach this origin along the x-axis, and that's if y was equal to 0. All right, so if I did that, I would actually be looking at the function f of x 0, because I'm letting y be 0 along the x-axis. And so f of x 0, notice, is just x squared. And in this direction, f is going to have I'm going to put this in quotes, it's going to have a minimum value in this direction. So if we're moving along the x-axis where y is 0, in that direction, f is going to have a minimum at the origin in that particular direction, because the 0 is the minimum value for the function x squared. However, we could also approach along the y-axis, and so that would be f of 0, y. So when I plug x d0 into the function, I get negative y squared. And so this would be an upside down parabola. And so in this direction, f would have a maximum value. Right? And so because the parabola negative y squared is a parabola that opens down, and the origin would be the highest point on that particular graph. And so in this particular case, we're able to pretty quickly see by picking two directions that are nice that we have a minimum in one direction and a maximum in another. And so what that tells us is that this function has a saddle point. At the origin. And since this was the only critical point, and all local extrema have to occur at a critical point, this particular function has no local extrema. All right, we only have this saddle point. Okay, so this example and the last illustrate two relatively simple functions, and we were able to classify all the local extrema, or in this case, determine that there were none. But it relied on the form of the function. The previous one was a very nice example where we were able to complete the square to show that that function value always had to be greater than or equal to 5, or to, negative 5. This one is one that it's pretty easy to determine directions in which we're going to demonstrate a minimum and a maximum value. You can imagine most functions do not have a property that you can handle in such a way. And so we're going to need some systematic way to check for local mins maxes or determine if a point's a saddle point. In single variable calculus, we used the first derivative test or second derivative test. There were two options for doing that. When we extend those to multivariable functions, the first derivative is not actually that useful. It's going to be used to determine the critical points. But what we're going to actually use is the analogous thing to the second derivative test. And so in the next video, we'll develop that and use it in some examples.